Let's review antiderivatives. And first of all, well, we know the integral of 3x squared is x cubed plus c. But why is this? Well, because when you differentiate x cubed, you get 3x squared. And more generally, if we take the integral of little f of x dx, we get capital F plus c, where capital F prime of x is this integrand, little f. This is the indefinite integral, and it stands for all antiderivatives. Okay, now, one comment I will make is about this all, or you could also just ask, why do we have the plus c? As a reminder, so question, y plus c? Well, an answer that's at least related to this example is, for instance, if we take the derivative of x cubed plus 4, or the derivative of x cubed minus pi, or the derivative of x cubed plus any constant, we get 3x squared, because the derivative of constant is 0. And so if you want all antiderivatives of some function, we really must have the plus c. Well, here are 3 indefinite integrals. And in each of them, you see a sum of some terms. And I'm using the property that if you have a sum of terms, well, you integrate term by term, just like we differentiate term by term. So here, maybe I will write this above in pink. This square root is a power rule. This is x to the 1/2, right? Power. And so when I go to integrate, I add a power, divide by the higher power. This becomes a 2/3. The integral of e to the x, okay. And then when you integrate a constant, you get the constant times x. And just like I was saying, don't forget the plus c. This term, this comes up often in Calc 2. This antiderivative for 1 over 1 plus x squared is the inverse tangent. You could see arctan x, but this is the inverse tangent function. And then ask yourself, what is an antiderivative for sine? Okay, don't say cosine. That's not right. The derivative of sine is cosine, but an antiderivative for sine, negative cosine. So we have minus cosine, and then plus c. In fact, you can check, right? Just look at this term, take the derivative. The derivative of cosine is negative sine, and then you have this negative, so in fact, we get positive sine here. And then for this last one, secant squared, this is one that is good to remember. How do we know? Well, the derivative of tangent is secant squared. So when you integrate secant squared, we get the tangent. And then this is not a power rule. Even though we see a power, when the power is -1, this is the one time with the power rule, well, does not work. An antiderivative for 1 over x was ln absolute value of x, so we get -3 ln absolute value of x plus c. Okay, so here are 3 examples, and every single piece, I will say, is something where you should know how to integrate. Here are 2 more examples, and these are both similar in that the best first step is to break them into a sum of 2 terms. So let's start with the first one. The first one does not involve substitution. We may write this as a sum of 2 integrals. Then we can use properties of exponents on each term. We have a 3 over x. Oh, we just integrated that, didn't we? And then we have 1 over x to the 3/2, but because I will integrate, let me write it like this. I write it as a power so that I can use the power rule. And then, as I mentioned, we just integrated 3 over x. Now I add a power, which will be -1/2, divide by the higher power, plus c. And typically, and I will say this the first day, it's not really good to leave fractions in the denominator. I am not a big simplify everything type of person, but you don't really want to leave a fraction in the denominator. This would be a good thing to simplify. And then this becomes -2. You can either write x to the x to the -1/2, or you can do this, put it in the denominator with a square root. Okay, now this is actually quite interesting, and it will lead us into more substitution problems. Now, if you start thinking, one place with substitution that we look for the inside function is in the denominator. And I'm going to say a lot more about substitution after I finish this problem, but this one is not too bad. If we take u to be 1 plus x squared, you see du is 2x dx. And I don't have exactly, not as it's written, 2x dx in my numerator, and this is why a similar technique of above is a good first step. Namely, we break it into the sum of 2 integrals. So I will break this into, and in fact, we just integrated that also. We got the inverse tangent, right? This is one to just know and remember what an antiderivative for it is. Okay, so now this term, maybe I'll even write this. I was doing my work in blue. The first one we will get, we get the tan inverse of x, but then we have this other integral, 2x over 1 plus x squared dx. And here is my substitution work, okay? We have u is the denominator, du, 2x dx. In my integral, I have 2x dx, and so this becomes, maybe I will move down here. Of course, the first term has not changed, but this becomes an integral. It's 1 over u du. So then I integrate, I get ln, absolute value of u, and then I would go back to x, which the last step is, if u is 1 plus x squared, then I just put in 1 plus x squared for u. And here, I mean, what's inside this is always strictly positive, so I can just turn these to open parentheses if I want, but it's also okay to leave the absolute values. Now, I think both of these came up on Calc 1 finals, which is one reason I wanted to do them today, the review day, where we're talking about integration and substitution. But I want to move into substitution, and this one I did a little fast because, we had exactly du in our integral. But let's take the time to write out the steps. What I have found, a lot of students, when they start Calc 2, they still have a problem with substitution. They don't quite yet have it down yet. And so today is the day to get it down before we move into other techniques of integration. Because, for example, we know substitution undoes the chain rule. In fact, maybe I can even write that. So let's talk about substitution. Now, we know if you take the derivative of a composition, we get derivative of the outside evaluated at the inside times derivative of the inside function. This is the chain rule. And this is why substitution is so important with integrals, because in Calc 1, how often do you use the chain rule? Well, almost every single time you take a derivative, right? Even if you're just differentiating e to the 3x, say, it's a chain rule. Really, that's happening. Okay, this is the chain rule, and so this means, well, I can integrate, and I get, if I integrate the left-hand side, I get that this plus c is, and I integrate this side. And this technique is called substitution. We see it on the board. Okay, I think about substitution as 5 steps. And the first step, maybe I will refer to this as I write, the steps that I always think about. First, I look for an inside function. U. Okay. Now, here, well, this is sort of inside. This is u, and then here, this is du. And in fact, that's what I was going to say next. The next step that I think about is I calculate du, which is, it's the derivative. Okay, so we differentiate. Well, we see it here, looking at his formula, but we differentiate. We differentiate u with respect to x and then multiply by dx. The third step, I convert my entire integral to an integral of u. Okay, and this part often comes with a multiplier, which we did not see in the last one, but we certainly will see in some examples. Then I integrate, and this is integrating with respect to u. And finally, we go back to x. We're handed a function of x that we want to integrate, and in the end, we need to hand back an answer that is a function of x, or whatever. Your variable might be t or s or whatever, but I'm listing the steps in terms of x. Okay, so these are my 5 steps for substitution, and I will run through them every time. Maybe for the first example, I'll actually number them, and then after that, I probably won't, but I'll still write the steps. Here is our first substitution example, and it also appeared on an old Calc 1 final. I think this is a very nice way to begin, because in theory, this is where we all are right now. So it's nice to work problems from old Calc 1 finals as we review integration and substitution. Okay, first of all, we see an inside function, square root of x. U is the square root of x, and then we have du. It's the derivative. Well, this is a power rule. But if we want to match up what we see in our integral, well, I'll do this for the first example, and then I don't always. But one thing you can do, because we know when we get to step 3, we convert everything to something of u. So you can write this part, so this will be, for example, sine of u. But let's just write this over here. And then everything else we can group with a dx. Like this. So this is kind of, maybe I will find another color. In my mind, I have this kind of grouped. And this is what I'm going to try to match up. So here I see square root, so let's just write this way. This is 1 over 2 square root of x dx. This is du. Now this is the multiplier part, okay? Handed to me in my integral, which is dotted in green, but handed to me. It's not exactly this. We have 1 over square root of x dx. And we want to figure out what the multiple is. Well, what can I do to this line to get here, just multiply through by 2. So 2 du is this. So what I'm going to do next, step 3 is coming next, right? Here, this will be sine of u. This will be 2 du. And this is really important when you're doing substitution. Every single piece of your integral gets converted to something of u, okay? You do not want to mix u's and x's, for example. So step 3, I have an integral, sine of u times 2 du. Then I integrate, and what is the integral of sine u? Negative cosine. So we have negative 2 cosine u plus c. And finally, step 5, we go back to x. Negative 2 cosine square root of x plus c. And this is our final answer, okay? So these are the 5 steps I think about, even if I don't number them. I think about them every time I do a substitution problem. Here's another example. Up inside the exponent of e, we have, well, 4 minus 5t. And this is one place we can look for an inside function. So u is 4 minus 5t. du is minus 5 dt. But we have just dt, which is negative 1/5 du. Sort of, well, you just divide both sides by negative 5. So this is typically, instead of numbering them 1 through 5, I will do this in a box, and then I just put equals. This is how I show my work, for example. So this becomes, well, it's an integral, e to the u times minus 1/5 du. When we integrate e to the u, we get e to the u. And so we have minus 1/5 e to the u plus c minus 1/5 e to the, and we go back to x. Oh, t, excuse me. This is an integral of t. We go back to t. So it's 4 minus 5t plus c. And this would be our final answer here. Now, I still have room on the board, so let's do another one. Maybe here. Okay. You see parentheses, and this suggests an inside function, but it's important with substitution that you have an inside function and we have a multiple of its derivative in the integrand. So here, 1 plus sine x, the inside function, the derivative is cosine. Derivative of sine, cosine, derivative of 1, 0, and so we have exactly the derivative in our integrand, and this is one reason that substitution will work in this situation. Okay, so my u, I see it, it's inside parentheses. U is 1 plus sine x. du is cosine x dx. And I have exactly du, so I don't have to solve for my multiplier here. So I have an integral. I could put a box around this if I wanted to. I have an integral. It's u to the minus 5 du. And then power rule. Add a power, divide by the higher power, plus c. And don't forget, we must go back to x, our original variable. So this is negative 1/4. Maybe I will put it back in the denominator. 1 plus sine x, like this. Okay, here is my final answer on this problem. Okay, now let's do some definite integrals with substitution. With a definite integral and substitution, you have really two choices. One, which is what I personally do, and you will see me do, well, in every video that I do a definite integral with substitution. One is, well, you convert the whole integral to u, meaning you have function of u, du, and these limits of integration are changed to u limits of integration, because right now they're x limits of integration. And if you do this, you change your bounds to u bounds, then you never have to go back to x. And this is an option, okay? The other option is, first, you just ignore the fact that it's a definite integral, and you find an antiderivative, find a capital F of x, and this would be substitution. You go back to x. Once you do this, then you evaluate at the x bounds. So these are two different ways to do it. Whichever way you choose to do is fine, it's up to you, but I personally would pick a way and do it that way the whole semester so that you don't mix the two ways. So for this very first one, which came off an old Calc 1 final exam, I will do it both ways. So you can see we should get the same answer, and then after that I will just always change my bounds, because this is the way that I know I won't make mistakes. The first way I will do is the change your bounds. Okay, u is, well, let's talk about it here. We see ln x inside parentheses, and more than that, the derivative of natural log is 1 over x. So we have a multiple, well, we have exactly the derivative of natural log in my integrand. Okay, so u is ln x, and then du, 1 over x dx. We have exactly du. Now, here comes the change your bounds part. When? So my x bounds go from 1 to e cubed. And what I need to change them is to u and u. Okay, and how do I do that? Well, when x is 1, u is the natural log of 1, which is 0. When x is e cubed, u is the natural log of e cubed. These are inverse functions. Ln of e cubed is 3. Okay, so this was my changing my bounds. Okay, now I'm ready to integrate. So this is sort of step 1, step 2, and now convert to an integral of u. Well, u goes from 0 to 3, and then I have u squared du. Okay, not too bad, right? This now, in fact, we don't see any ln's or e's anymore. This is just integrating u squared between 0 and 3. We have u cubed over 3 evaluated between 0 and 3. Well, when we evaluate at 0, we get 0, and so this is just 9. Okay? So this is way number 1. Now, I'm going to take the time now to say this again, or stress this, because what's really important, whether it's definite or indefinite, is that you never mix u's and x's in the same integral. That doesn't make sense. So here, function of x, my differential is dx, my limits of integration are x limits. And this is a number, right? Every definite integral is a number. It's a number. Well, it's 9. We calculated it another way, but this is a number. And here, function of u, differential du, and u limits. So you never see me write down something that has u's and x's mixed together. You don't want to do that. But here, well, let's start. Here I'm doing this. Indefinite integral first, okay? And I'm disregarding limits of integration. But I have the same start. U is ln x, du is 1 over x dx. I can make a box. And I get the integral of, well, it's u squared du. I integrate like this. Oh, no. I go back to x. Now I go back to x. So I have ln x cubed over 3 plus c. Okay, now I'm finished with the first part. So this way, we do have to go back to x, and that's the whole point. We find an antiderivative first, And then once we have that, maybe I'll switch to another color. Now we have an antiderivative. We have a capital F of x. So we can then, if we want to go from 1 to e cubed of ln x squared over x dx, we have an antiderivative. And we evaluate between 1 and e cubed. X, limits of integration. Okay, because this is a function of x, I went back to x. So I get ln of e cubed over 3 minus ln 1 cubed over 3. And just like before, ln of e cubed is 3. So we have 3 cubed, 27 over 3. This is 9 minus 0. Okay, we get 9. Same number, but these are two different ways to do a definite integral using substitution. Here's another definite integral that is substitution, and we know it's substitution because here underneath the radical we have 4 minus x squared inside function, and we have a multiple of its derivative in our integrand. So let us begin with u is 4 minus x squared, du is minus 2x dx. Now we have x dx, which is, well, if we take this equation and divide by -2 or multiply by -1/2, we get the lower one. So we have -1/2 du, and this says x dx. So this is what's handed to us in our integral, and then I will change to u limits of integration. So when x is 0, u is, well, 4 minus 0, okay? And when x is 2, u is 4 minus 2 squared, which is 0. Okay, so here I will put this box. So now if I go back to my integral, I have everything to convert my integral to an integral of u. It will be an integral. It goes 4 to 0 of, well, I'll write it this way, u to the 1/2 times minus 1/2 du. Now, one thing we know about properties of integrals, we could interchange the limits of integration, and it would read 0 to 4, and this would multiply through by a minus sign, but it's fine. I will leave it like this. We add a power, and when we divide by the higher power, it multiplies by 2/3. And then we evaluate between upper limit 0, lower limit 4. Now, when you evaluate this as 0, we get 0. So we just have minus, and then evaluate at 4. This is 1/3, and we have 4 to the 3/2 power. We can take the square root of 4 and then cube it, for instance. We get 8 divided by 3. And this is our final answer here. Here's another definite integral, and again, we see the tan inverse. But here, we're gonna have to remind ourselves some things about the tan inverse. Every time you see the tan inverse, you should think a few things. First of all, you think about its derivative, which is 1 over 1 plus x squared, and in this function, we have the derivative. So it's very natural to have u is tan inverse, and then du is 1 over 1 plus x squared dx. In fact, maybe I'll write that before I do anything else. U is the tan inverse of x. Du is 1 over 1 plus x squared dx. But another thing, and this is a good review just as we start the semester, when you see the tan inverse, let's think about the graph. So tan inverse lives between pi over 2 and minus pi over 2. Okay, asymptote here, asymptote here, and as you go to minus infinity, or the limit as x goes to minus infinity of the tan inverse is here, this minus pi over 2. And then it comes through the point 0, 0, and the limit as x goes to infinity of the tan inverse is pi over 2. So this doesn't look that readable here. This is minus pi over 2 is this, okay? This is the tan inverse. Y is tan inverse of x. Okay, well, I'm going to change my bounds because for me, this is easier. So let's do this now. When x equals 0, what is u? And when x equals 1, what is u? Well, now we have to think more about what is the tan inverse. The tan inverse, you feed in a tangent value and it gives you back an angle, right? Well, we see from the graph, it passes through 0, 0, and so that part is the easy part, or easier part. But here at 1, this says the tangent is 1, and the angle is between minus pi over 2 and pi over 2. So if we think about our unit circle, the tangent is 1, and you're between minus pi over 2 and pi over 2. That happens here, where sine and cosine are equal. It happens here, pi over 4. So that is this. When x is 1, u is pi over 4. Pi over 4. Okay, so this is my substitution work. And now, let's integrate. So now I have an integral with respect to u. Maybe I'll write it here. So this equals what I will write here. It's an integral. It goes from 0 to pi over 4. And we have, well, it's just u du. Okay, u squared over 2 evaluated. And we get pi over 4 squared over 2, which is pi squared over, let's say we have 16 and 2, 32. Okay? So I was just talking about the tan inverse. We saw it here. One reason it's so important and comes up a lot is because integrands that have terms of the form 1 over 1 plus x squared, these appear in partial fractions, which is later this week. But another thing that also appears is something like this. Or maybe let's, should I put a number or leave it as a? Let's do a number because we're integrating. First day of class, let's integrate numbers and not have like a variable letter in it. Okay, 1 over x squared plus 4. Now, this looks like the tan inverse, except instead of a 1, we see a 4. But we can figure out the integral of this using substitution. So let's rewrite it first, because as it's written, I don't really see an inside function and a multiple of its derivative. What I can do is factor out a 4, and then I have, this would be x over 2 squared plus 1 dx. Now, make sure you believe me, because look, well, maybe I'll show you my side work over here in case you don't. Because what first I could have done is write it like this, right? Which is definitely the case. You factor out the 4 and this would be your first step, but then 4 is 2 squared, and so I would march to this step. Okay, so when I have factored out a 4, then I have this. Okay, maybe I'll leave that up for the moment, it's fine. Now, if you look at this integral, now you see something inside parentheses, right? And it's going to be nice for substitution, because if this is u, The 4 or 1/4 I can pull out, not a problem. If this is u, then you see what I have. I have a u squared plus 1. And this would be the tan inverse. This is the idea behind this integrand. Okay, so let us do this. Then we will do I'm going to make a few more comments, examples, things like this, and we will be done with the review, and we will move into what's next? By parts, which is a lot of fun. Okay, but in any case, we will work on this for the moment. Okay, so if u is x over 2 is what's inside my parentheses, then du is 1/2 dx. Now what do I have? Right, in fact, maybe this one I will rewrite so I see it. I did this in one example, but I'll rewrite this one as well. And then times, I could write it as the 4th being here. So you see here, right, what do I have? I have 1/4 dx. Now, I will say this, trying to figure out the multiplier, to go from something like this to something like this, this is the step that when I was a student, I missed the most. When my professor taught me, well, you look at it and you multiply on one side by one thing and multiply by the other thing, and then you have it. And I never got it. If the multiplier is supposed to be 2, I would write a half. If it was supposed to be -4, I would write -1/4. I always had 1 over what was supposed to be this multiplier until I started just writing out du, writing out what I have. So this is what we have handed to me in my integral. It's right here. And then I would just compare the two equations and see, because this should be some multiple of du. Then I started getting it right. So here, if a half becomes 1/4, we are multiplying by a half. And you could check. If you multiply this first equation by a half, you would get exactly the bottom equation. Okay, so I have an integral. Oh, I meant to keep it with this color. It's an integral. It's 1 over u squared plus 1 times 1/2 du. Now we can integrate. This is a half tan inverse of x over 2 plus c. Okay, so one thing that you see from this, you could go through the steps every time, but one thing that we see from this, for example, anytime you have an x squared plus a squared, so what we see, this is the one I started to do and I changed it to numbers, but we would get, well, if you imagine going through this with the a instead of a 2 squared, this is 1 over a tan inverse of x over a plus c. And this is something you can just use, for example. If you see a term like this appearing in a partial fractions problem, which we'll get to later this week. Okay, so if we integrate, I'm just going to do a few examples. Cosine of ax dx, or the integral e to the ax dx, or the integral, let's see, what else can we put something? Oh, secant squared ax dx. Okay, I'm trying to think of ones you should know the integral for. Maybe I'll put the sine. Okay, fine. Ax dx. Okay, well, all of these have something in common, which is that the inside function is a times x. Okay, now, we have to think differently. You should or can, instead of running through substitution every single time, you can just remember how it goes. So if we were differentiating, let's do this one for example. It's a chain rule, and we take the derivative of the outside function, evaluate it at the inside, times derivative of the inside function. So you see we get minus a sine ax. This is the derivative. Okay, well, I see a lot of people mistakenly just multiplying by a when they integrate. So for example, they would integrate this one and multiply by a, something like this, but it's not like that. So let's see what it is. Well, it's really substitution. Okay, so in any of these, u is ax, du is just a dx. A is a number here, right? Now, if I have just dx, this is a 1 over a du. And now you imagine going through the steps of substitution, you're going to have this 1 over a multiplier, okay? So this is something that would be the initial part. You could work through substitution. So for example here, the 1 over a multiplier, this would be the integral of sine negative cosine. So this one would be 1 over a negative cosine ax plus c. The integral of secant squared, it's the tangent. This would be 1 over a, the tangent of ax plus c. The integral of e to the x, well, e to the x, this one would be 1 over a, e to the ax plus c. And finally, if we did something like this, cosine ax, you integrate cosine, you get the sine. This one would be 1 over a sine ax plus c, like this. So when you see this number, it could be 5x, 7x, whatever, minus 2x, negative 0.1x, whatever it is, on the inside, what happens when you integrate, a 1 over a comes out of it. Now, I wanted to make that comment, even though I said the first day we weren't going to be integrating letters, but this is it was still good to say, because this is something that if you remember, you don't have to go through the steps of substitution every single time. Okay.